Hello, chemists. It's Jolly again. More kinetics. Yay! All right, this time we need to talk about the linear equations and concentration versus time. Now, everything we've talked about in the past, concentration versus rate and just the overall rates, those are neat, but we need to be able to have something that we can test in the lab. And concentration versus time is one of those. Okay, time is an easy thing to test, but rate isn't so easy. So these are very useful reactions, and they're going to turn out to be straight lines. But we have to do some extra math in order for it to be meaningful for us. And so we're going to have to look at each of the orders individually. So in order to do concentration versus time, I'm going to do every order, but we'll start with the first order. In order to make a linear line so that we can have a slope, you have to do special math. Sometimes it's a log, sometimes you invert it. Okay, it's just math function. It has nothing crazy or anything to do with chemistry. But what we're going to do is we're going to use calculus, and we are going to integrate from 0 to time t. And because of that, we're going to get some different functions for each of them. So if we're doing first order and we integrate from 0 to time t, we end up with something like this. The natural log of the initial concentration. Okay, so that's the initial. The concentration at some time t, and it equals to kt. Well, we need to put it into some kind of a format that we can use for a straight line. So we are looking for y is equal to mx plus b. So is there any way that we can manipulate that and get that linear equation? And the answer is yes. All right, you don't have to remember the log rules, but if you ever have a log of something divided by something, that is the same as the natural log of the initial minus the natural log at time t is equal to kt. And remember, this is the dependent variable. This is the independent. That's the intercept. And that's the slope. All right, what piece is what? Okay, let me change colors here. The M is the K. X is the same as T, so I just need to figure out which one is Y and which one is B. Well, of course, the one with the subscript T is the dependent because it's dependent on time. So I'm going to manipulate this around, and I'm going to get this one on the left and these two on the same side. So that gives me negative natural log of some time t is equal to kt minus the natural log of the initial. But in the straight line equation, I do not like the y variable to be negative, so I'm going to multiply through by a -1. And I get the natural log of the concentration at some time t is equal to a negative kt plus the natural log of the initial. And guess what? That is beautiful. This is y, this is m, t is x, and that whole thing is b. The power of a straight line is we can get the slope, and for us, the slope is the rate constant. And so this is what a graph would look like. The natural log of the concentration, and on the x-axis would be time, and this is a linear line. Okay, now the dots are all experimental data. And of course, these look perfect because they're not really experimental. Real data would look something like this. And you'd have to do a scatter plot in order for it to work. So what we need is the best line fit through the data points, and that will give us the straight line equation. And we can either figure out the slope and the intercept by hand, or we can have the computer do it using regression. And so that's what we're going to do. We had the computer work it out for us. And so we now know the slope and the intercept, which means we therefore know the K value and the initial concentration. Another thing that we can get from this linear equation is the half-life. Because if this is our equation, okay, y equal to mx plus b still, and I want to know what the half-life is, well, then we know we want the concentration when it's half of the original concentration. So I plug that in, these two go away, and I'm left with the natural log of 2 is equal to K, and it's the half-life. So this is the equation for a first order half-life. Now I want you to notice only the rate constant is inside here. There's no initial concentration. All right. Let's go to the whiteboard. And let's do an example. Where is my whiteboard? There you are. All right, let's do an example of this graph per se. All right, so I have a set of data and I have concentration and I have time. All right, and I'm completely making these numbers up. So we'll say 0 0.10, 0 0.09, 0 0.08, 0 0.07. Now I'm making these up so they look linear. Point, do you want to go any further than that? Oh, that's what looks funny. That's a 7. 6, and we'll say 5. And we'll say 0, 10, 20, 30, 40, and 50. All right, so let's say we graph this. And it turns out concentration versus time, and it comes out as a slope. The problem with that is I can't get an intercept and I can't get a slope unless I just choose one line or one spot and draw a tangent line. Okay. Not useful because I need something that will work for all sets of data. So like I mentioned before, is there any mathematical way to manipulate this data? And the answer is yes. So in math, you can do many things, and one of them is probably going to come to be a straight line. All right, so how about if I take the natural log of that concentration? So I literally plug in the natural log of 0 0.10, the natural log of 0 0.09, so forth and so on, and then I graph that. If this comes out to be a straight line, okay, then the answer was yes, I am first order. So when I manipulate the data to be the natural log on the y-axis versus time on the x-axis, and it turns out to be a linear line, it is telling me, oh, this data must be first order, and I can get the slope and the intercept either by the old-fashioned way, the calculations, or I can get the calculator to do it, and I can plug those in, and I can use that data. Now, I know that's very vague right now. I have to show you the other two before we can really put it together. All right, so that was first order. We're going to do the same thing with zero order and second order. All right, so the rate law for zero order would look like this. So basically that goes away as a 1. So we're going to integrate that from 0 to time t, and we are going to end up with this straight line equation. Y is equal to b plus mx. So if we want to turn it around, the concentration at some time t is equal to a negative kt plus the initial concentration. And it doesn't matter what order you have it in, but this one just looks nicer. So y is equal to mx plus b. And guess what? We could do half-life for this one as well. And then second order, we would integrate its rate law from 0 to time t. And this is what it spits out at us. And again, I have to get it into y is equal to mx plus b format. So the concentration at time is the y, the initial is the b, the k is the slope, and the t is the x. So if I manipulate this, I should come up with 1 over the concentration at some time t is equal to kt plus 1 over the initial concentration. And again, I can plug it in and get the half-life. So these are on your reference sheet, not quite as detailed, but here's the order, This is what the rate law would be, okay? Here is the linear equation. Now notice I haven't manipulated them into y is equal to mxb format for you here. And your half-life equations, all right, like I mentioned before, notice zero order, you have to take into account how much you started with. Second order, you have to take into account how much you started with. First order does not depend on your starting material. Okay, so the half-life does not depend. If it's going to be linear, concentration versus time is what is for zero order. Natural log versus time is for first order. And inverse versus time is second order. And so if those turn out linear, then you know which order it is. And we're not go here. Back to the whiteboard. All right, before I show you some example graphs, we're going to use this data some more. Erase. All right. So this is the data that I've had in the lab. Okay, so pretend that the numbers are something that works out perfect. All right. So my first question is, hey, I need to know if you're zero order. I need to know if you're first order or if you're second order. Okay, those are the ones that we're going to play with in this class. And so I'm going to manipulate the data. How am I going to manipulate that data? Well, I know if I want zero order, I'm going to graph concentration versus time. Well, I already have those two pieces, so I could graph right now if I wanted to. In order to do first order, like I mentioned just a moment ago, you would have to take the natural log of that concentration. So we would ask the computer, or we would do it by hand. Yeah, you're laughing at me. You would just put it in a computer or calculator. Okay, so forth and so on. And then I would graph these two if I was asking if it was first order. These two, I'm asking if it's zero. And what about second order? This one would be natural log of concentration versus time. And this is 1 over the concentration versus time. So I'd have one more column and I would divide it. So 1 divided by 0.10, 1 divided by 0.09, so forth and so on. And I would graph that, and that would be asking if it is second order. Now, it can only be one of them. There's no way for it to be both. So we do our little graphs. So concentration versus time, natural log of concentration versus time, and 1 over the concentration versus time. And again, completely making this data up. Curve, straight. Right, it all depends on what we were asking the math to do. And so this question, I'm asking the math, are you zero order? And it is not linear, so the answer is no. Okay. Are you first order? It is not linear, so the answer is no. Are you second order? It is linear, so the answer is yes. So this data is from a second order reaction. And so I don't care about this data anymore, and I don't care about this data anymore. What I really need to be looking at is T and 1 over the concentration of T. And I want you to notice this has a positive slope, whereas the examples for zero order and first order should have negative slopes, and that's taken into account in the graph. All right, well, what am I going to do with it? Yay, I'm second order. Who cares? I am now going to manipulate the data. I'm going to do linear regression either by hand. I'm going to have the computer do it, something. And again, I'm making these numbers up. It is going to spit out, hey, your slope is 0.050 and your intercept is, trying to make this up off the top of my head. All right, completely making it up, but 2.3. Okay. All right. What am I going to do with those? All right. First off, can you write me a generic rate law? Yes. I know that the rate is equal to K to the second order. Okay. So I know that, but it would be awfully nice if I could figure out what K is. Well, what data do you have? We have time and we have concentration. So that's the linear equation. And I know it's second order. So here's the equation for it. That begs the question. That still looks like a whole bunch of variables to me. But guess what I can get off of the graph? This is slope. And this thing is the intercept. So I actually know those two pieces. So 1 over the concentration at some time t is equal to 0.050. Now remember, we know what the units on a rate constant should be, and this is second order, so it should be 1 over molarity time, 1 over molarity time, times t, oh, we run out of room, and plus 2.3. I now have an equation that will relate together concentration of time, concentration at some time versus you plug in a time and it will spit out a concentration for you. And that is the power of the linear equations. Do not get hung up on this math. Okay, that really has nothing to do with chemistry. That is the manipulation of data to try and get a straight line. And the only reason we want a straight line is so that we can get a slope on it. Okay, we could do crazy math. We could take the tangent of it. We could take the, I don't know, the log base 10 of it. We could just manipulate it any way until we got a straight line. It just happens to be that these variables and these conditions match zero order, first order, and second order. All right, before we're done with this one, let's run back to our notes. All right, when I manipulate these, this turns out to be A at some time t is equal to a negative kt plus the concentration initial. If you will notice, different color here. If you will notice, there is a negative in that equation. That negative is because the slope will always be negative. It is part of the equation. When you manipulate first order, it's the natural log at some time t is equal to a negative kt plus the natural log of the initial. And again, there's a negative because the graph will always come out negative. But second order, because it is inverted, does not. It has a positive slope. And that is why there are positives and negatives in the equations so that it accounts for what the graph is actually doing. Now, right now you're thinking, thank you, I still don't know what to do with that. We're going to manipulate it in another video because then we're just going to do examples. So this gives you a rough feel for, hey, if you want to play with the variables, concentration versus time, you have to manipulate the rate law into something that will give you a linear line. And for first order, that happens to be the natural law. For zero order, it's just the concentration. You don't have to do anything to it. And for second order, you have to invert it. And that is the power of the linear equation from the rate law. All right, until next time, jolly out.